Good afternoon and welcome back to the 36th Annual Crestone Energy Fair's presentations. I am very excited to announce Ronald Rael, who is an architect and visionary artist who hails from Conejos County, just a few counties down the road. His work defines disciplinary boundaries, and he's internationally recognized for projects that fuse cutting-edge technology with deep social and environmental consciousness. Rael reimagines a new architectural paradigm where technological innovation and cultural memory are not at odds, but intimately intertwined. So, come on, Ron. Thanks a lot.
Thank you for that introduction. It's really a pleasure to follow Professor Peña because I wish that I could someday make architecture in the same way that he engages food. And I think we have a lot of very similar philosophical alignments. And so if you were there for the previous lecture, I'm hoping I can kind of build upon many of the things that he said. But one thing that's been on my mind lately quite a bit is this notion of AI. And many of you have been thinking about AI maybe, and what is AI? There are three kinds of AI that I want to talk about today. The most important one to me is ancestral intelligence. The second one is additive intelligence, and I'll talk more about that today, which has to do with additive manufacturing, or what is more known as 3D printing, and of course, artificial intelligence. One of the things that Professor Peña talked about was how the food culture of the southern part of the valley is very much a fusion of different cultures coming together, as are the people, as is our language. And one of the reasons is because the San Luis Valley was the northernmost frontier of Mexico prior to the Mexican-American War. These were the borderlands of the United States and Mexico. So much of my own work builds upon the idea that borderlands are not a space of division, they're actually spaces of coming together. Sometimes things come together in beautiful ways, sometimes in violent ways, sometimes in ridiculous ways. So I like to think about how many of the traditions that we have, when infused with something else, become something very special. As an architect, one of my main passions is working with the material of the landscape. This defines the landscape, especially in northern New Mexico and the counties in the south, which are buildings made out of adobe. Adobe is mud mixed with straw and water, and it's been used for thousands of years in this region to build buildings, and for 10,000 years on our planet. In many ways, it's the most sophisticated building material we have. If you put a bunch of material scientists in a room and say, come up with a building material that's inexpensive, that's non-toxic, that you can recycle, that responds thermally to its context, which is locally available, which can be recycled back into an environmentally safe material, these material scientists would spend millions of dollars trying to figure out what this is, and they'd probably never come up with it. But human beings have been working on that problem for 10,000 years, and they have arrived at that, and that's buildings made of mud. I've taken on a project that I call the Adobe Archipelago, where I'm trying to save the remaining adobe building culture that we have in northern New Mexico and southern Colorado. And I'm currently stewarding about 15 different adobe buildings of different historical importance. Some of them are very important, for example, an Indian agency in Conejos. Some are cultural heritage sites, like this, which has an active morada, oratorio, a 2-story farmhouse building. My own great-grandmother's sister's family's house, which I use as a test site for teaching traditional and indigenous building technologies, how to earth and plaster in traditional ways, how to make adobes, how to make hornos. I tap into traditional cooking traditions as well that were practiced by my family. But there is an ethos around thinking about what is in the landscape and how can we build with that material. So I host workshops often that connect people of earth and heritage practices back to these practices that have been disconnected from their traditions because of capitalism, because of their lifestyles are changing, because of assimilation. And so earthen architecture practices aren't continued anymore because of changing in code regulations and building regulations. So I teach these classes on how we can reconnect ourselves through the maintenance and restoration of these buildings. Also, as an architect, I design buildings made of Adobe, contemporary buildings. This is probably the first Adobe building built in Marfa, Texas in 100 years, called the Box House, entirely made of Adobe, plastered with Adobe on the inside and on the outside. The bricks on the bottom come from New Mexico. The bricks on the top come from Ojinaga, Mexico. So it's also, there's a future archaeological project or anthropological project or geological project built into this house that connects this house to borderland landscapes. I also think about how there's a politic embedded in building with earth. Not only the politics of working with codes, but also the politics of being activists that want to hold true to these traditions of building, and how Adobe buildings can be a political project. This was a project I collaborated with two artists from Europe called Prada Marfa. It's not an actual Prada store. It's a sculpture. It's an installation built in the Chihuahuan Desert in the middle of nowhere, but it holds the 2004 line of Prada shoes and purses. So there's a paradox in this building. There's a paradox about this building being in the borderlands, about a site where people walk hundreds of miles to come to the United States, a site where these shoes that cost in excess of $1,000 are on display, and talks about the borders between wealth and poverty in the United States, particularly in the borderlands of Texas and Mexico, and the contemporary borderlands. A building we made out of Adobe to demonstrate again that juxtaposition between wealth and poverty, between contemporaneity and history and tradition. We set each Adobe brick in a cementatious mortar, not because that's a better way to build, but because that's what the US military used to build forts after the Mexican-American War along the Texas-Mexico border. And you can see those buildings in Marfa, Texas, and how time has taken a toll on, in fact, eroding the Adobe faster because it's set in an impermeable layer of cement. In fact, this wall just collapsed recently, I was told, after being there for maybe, I don't know how many decades or close to 100 years. But these are expressive ideas about how we can communicate politics, tradition, culture within a very single, humble material. If you've been to the town of Conejos in Conejos County, I've been working with the community there for 19 years to design and construct this labyrinth as a site of internal reflection, of prayer, of spiritual contemplation. And it finally was completed this year after 20 years. The community made over 40,000 adobes to build this structure. We taught the community how to make adobes, for those who didn't know how to stack them, how to lay them. And after 20 years of slow process, this came together. And you can see, this is photos from several years back when it was still under construction, but you see the building in the winter. And to get a sense of scale, you can actually see me walking into the building, if you can see that, on the lower part of the labyrinth. So you can see how enormous it is. It's a really quite amazing phenomena created by the community there in and around Conejos. Obviously, I have an obsession with earth and architecture. I try to share this with the world. I have a website called eartharchitecture.org. You can go to that website, and it's kind of a repository of earth buildings from all over the world. Because earthen construction is actually what connects us across the planet. People build in New Mexico in the same way they build in Mali, Africa, in the same way they build in Yemen, in the Middle East. On every single continent, you can find similar construction processes and methodologies. In 2008, I also wrote a book called Earth Architecture, which talked about earth being a modern building material, a building material that can connect us to, at that time, our 21st century lifestyles. And In the very end of the book, I wanted to talk about what the potential future of earthen construction was. I talked about how the internet was connecting us and shaping the way we can inform each other about earthen construction practices. But there was a novel technology that was emerging called 3D printing. There was one professor who kind of invented this at the University of Southern California, who was printing with concrete. First guy to do this back in 2007. Now it's getting more standardized. You've probably seen it on television. But I imagine that maybe the future of earthen construction is actually robotics as well as additive manufacturing. And the reason I believe that to be true is because if we think about additive manufacturing as maybe the quote-unquote most advanced way of building a building, I thought maybe we shouldn't be using a building material like concrete, which has proven over the last 200 years to be incredibly detrimental to our planet, but instead use the most sophisticated building material on the planet, which is earth, which is the soil right beneath our feet. After I wrote that essay, I thought, well, maybe I could try to do this. I come from a tradition of building with earth. My father built earthen buildings, my grandfather, my great-grandfather. You can probably trace it back for thousands of years of continuously living in buildings made of earth. So I embarked on a journey to see if I can figure out how to use robotics and computation to make buildings out of earth. This began in 2009. It's been a slow process, but I'm trying to figure out how we can take humankind's oldest additive manufacturing technology, which is earth, and create structures using computational design, digital design. And we had lots of successes in using clay and being able to use additive manufacturing to make objects like this. They were very fine and detailed, and because they were so fragile, we began to fire them and make ceramic objects. And I wondered, well, what does a robot, if a robot can make ceramics, what do we do? Do we make bricks? Do the bricks hold plants? Do we make bricks that have air pockets that can hold insulation? Can we build upon traditional ancestral intelligence to think about how we can transform simple things like some of the earliest swamp coolers, which were made out of very porous ceramics, that were often placed in a window where cool breezes came over that humidified the air, lowered the temperature in a building? And could we make bricks that could do the same thing, that could hold water, that can pass air through, humidify the air? And so these are some of the first 3D printed bricks that were highly porous, that had micropores that could hold enormous amounts of water, but also larger pores that air could pass through and ventilate a space inside, that had a tensile component to the way the mortar attached, and had shading elements that kept the water from evaporating more quickly. I called this the cool brick. So started to use clay, started to experiment with sand, began to think about how we could make objects made out of sand. And this is at a time when 3D printing was in its infancy, and it was very expensive to print a very small object with a 3D printer. A small object as big as this microphone might have cost $80 to make at that time. But because we developed this material using sand, it became very inexpensive. And I began to imagine, well, what could buildings look like if they were made out of this material? But also, I was making models. Then I realized, oh, I can make assemblies. I can make assemblies of parts that could begin to make walls. And so these are some of the earliest studies made out of sand, thinking about how we can create an aggregation of objects based on the dimensions of the 3D printer that we had, and make much larger objects that attenuated sound, that responded to structures, and also always looked back to the ancestral intelligence that were embedded in our knowledge base of construction. And so if you're familiar with Incan ashlar masonry, you find this in Cusco in Peru, these interlocking stone blocks that are very difficult to achieve. It demands incredible craftsmanship to make blocks like this. This one, I think, has 13 corners of interlocking these blocks very tightly. But we could maybe 3D print earthen blocks. Those blocks in Cusco actually respond to earthquakes. They're very seismically resistant to earthquake forces. Could you create blocks that do the same thing with a 3D printer, that allow them to be interlocked, that have instructions embedded in them, that has handles on them, so you could quickly build a structure that's seismically resistant using the building material right beneath our feet? This journey of thinking about local materials and this ethos about Adobe allowed my studio to expand the possibilities for what else might be considered local, as a local material. And he began by just looking around the kitchen, the things we throw away, like coffee grounds. And we began to invent a material for 3D printing that used coffee. And this isn't, sometimes if you're familiar with 3D printing, there's a lot of plastic 3D printing materials that are available that put a little bit of coffee or a little bit of wood or a little bit of some material so it kind of looks like this. These are 70% of that material. So that's 3D printed coffee. Those are 3D printed coffee cups made out of coffee grounds. You also saw a teaspoon made out of sugar, but it didn't make sense to make the teaspoon out of sugar, so we wondered if we could make teaspoons out of tea, but we made teacups. We made a teapot that was based on the first pot ever. The first object that was ever translated from a physical object to a digital object was this teapot called the Newell teapot, or the Utah teapot, because it was developed at the University of Utah. If you ever watch any Pixar movie, they always put the Utah teapot in it because the technology that was invented to develop Pixar actually came from the University of Utah, where this first object was translated digitally into the computer. So we made that object physical, out of tea, bringing it back into reality. So teapots, teacups. And I don't show the teaspoons, but we made teaspoons also out of tea. In Northern California, where I live part-time of the year, of course, the wine industry is there in Northern California. And they produce an enormous amount of grape skin waste in the production of wine. And they dry it, it becomes powder. They try to sell it to humans to put in food. Humans don't like it too much. They try to feed it to animals. Animals don't like it too much. But we experimented to see if we could make a material for 3D printing out of this waste product. And so these are Chardonnay grape skin objects and cups that we made out of that. Not only other biological-based materials, paper made from paper pulp and paper waste, newspaper waste in this case. These experiments made of paper pulp evolved to the point where we could begin to print with sawdust. And in the US, we produce like 7 million tons of sawdust a year from the construction industry, and it usually goes into landfill. So this became a very productive way to think about how we could use this sawdust, not in a subtractive way. And what I mean subtractive is that we have a forest, we cut down trees, we take those trees, we subtract them, we make boards, we subtract them, and we make boards that are used for construction when we chop them up. And ultimately, we're left with a lot of sawdust. Could we use this additively to imagine the way we can make new products in the future? And so we developed a 3D printing material made out of sawdust, and always imagining how we could maybe make building facades, components in automobiles, screens, any kind of object just made out of 3D printed wood. And it became very, very successful. We actually started this company and sold this company. We called it Forest. We believe that the forests are for us, so we should save them. And unfortunately, when you sell a technology, you think that all of a sudden that technology is going to take over. And I was very excited and said, now I can print anything. I'll print a house. That was our first project after we sold this company. And instead, this company decided to shut it down. Just like they bought it, and they don't want to do anything with it. Sometimes companies do that. They don't want something to go to market, or they don't want to go to market yet. So that was a lesson in thinking about what it means to develop intellectual property and attempt to bring it into market, and the kind of trust you might have in companies in order to think about the future of construction. Other materials, salt. In Northern California, if you ever fly into San Francisco Bay Area, you see these beautiful colored ponds. They're actually um, they're microorganisms that are responding to the brackish water, where they fill up these pools, and over the course of a year they dry and they produce hundreds of thousands of tons of salt. So it's a material produced by wind and sun, and we developed a 3D printed material made of almost pure salt. And all these materials, when they come out of the machine, they're actually edible, except for the wood. Yeah, I guess you could eat the wood if you wanted to, but they're totally non-toxic. In some cases, we would coat them with a sealant made out of bamboo that was developed at the University of California. So it's like a low VOC polymer. Every single wood product in your home is coated with a polymer, but they produce a lot of gases. This one, in fact, came from a recycled bamboo product. But because some people ask me, are these waterproof? And in many of these cases, they actually are, and these epoxies actually strengthen them. So this is an experiment of salt. So we're beginning to think about how we can scale up other materials, car tires, cryogenically frozen car tires that are pulverized, developed into a 3D printable material. And these are some of our experiments that came out of our studio. And of course, cement. And that's where the 3D printing industry has gone. But we developed a way to produce objects with cement that used very, very little water and no formwork whatsoever. It can make very complex objects, very thin objects. The cement was even translucent if we could print it that thin, about a 1/16 of an inch thin, and extremely lightweight. And so lightweight that they become, you couldn't pick up a concrete ball this large, but these were very lightweight objects that could be assembled very quickly. And so these aggregations allowed us to assemble furniture, partitions, spaces, objects. And one of the beautiful things about this way of working is that if you are a designer or an architect, you typically create a set of instructions for someone to craft or build the thing that you want to build, whether it's a building or a piece of furniture. But the beauty of this is that you can design this in the computer and go straight to manufacturing, straight to construction. So the very same information used to create this model was the very same information used to create this space, this object. And extremely complex. Every single one of these is an experiment in a way of working and exploring the possibilities of additive manufacturing. In this particular instance, these experiments very much had to do with the notion that you could disassemble and assemble an object quite quickly, and just a few people could assemble this room in just a matter of 15 minutes or so. So it was an incredible diversion that lasted many years, that we began with earth and ended up with salt, wood, rubber, car tires, all these things. But the idea was that we would always return to a way of thinking about how we could scale up the possibility of printing with earth. One of the requisites of this was to have a higher degree control of the movement of a robot to deposit earth in a particular way. And about 8 years ago, we started on a project that began to 3D print with ceramic clay, and we started to create these very weird objects. And this was a very different journey that we embarked upon, because we are not ceramic artists, but we had invented a way of placing clay down that didn't follow the rules of 3D printing. The rules of 3D printing is that you're making an object in the computer, and the idea of that with a robot was to make the exact object that was in the computer. But instead, we found that the glitches were the most exciting part, that you could deviate from the making of the object to make objects that had incredible textures, new kinds of possibilities that responded to the gravity and plasticity of the material. The same way that you would do with your hands when you're building a building made of adobe. You might experiment, you might push, you might leave your handprints in it. In a way, this is leaving a digital handprint based on errors that we calculate into the making of these objects. Not knowing what these are good for, just that they're really beautiful and interesting in a very scientific way or in a very artful way. And we explored ways of making ceramic objects with incredible textures, um, different kinds of forms or shapes. And you might think these are all vases, but they're not vases. What these are all are studies in the movement of a robot depositing clay. They're mathematical formulas that become material. And we began to think about, okay, well, how can these become building materials, and what are they good for? Could they become facades? Could they become new kinds of cladding systems, micro shading devices, shingle devices? The politics of printing with clay also entered into this. I don't remember when this was, like 6 years ago, we were invited to explore this idea at the University of Arizona's Rubin Center. And we asked if we could invite 25 ceramic artists from El Paso and Juarez to participate in using robotics to make ceramics. And we worked with the geology department at UTEP, and we went around looking for traditional clay sites, and we found this incredible spectrum of clays that we used that were found both in Juarez and in Texas. So they're this binational borderland ceramics, and the potters produced over 250 ceramic objects using local clays, found both in Juarez and El Paso. We pushed this idea further, of this idea that an object, sort of like Prata Marfa, has a politic embedded in it because the soil has a politics embedded in it. Whether the soil is contaminated by something that happened, whether the soil lies in Mexico or the United States, or it's blended together to become a fusion. And so we created a series of objects based on something that our president said when I was in El Paso. He said there's a lot of bad hombres at the border. And I was there in El Paso at the time, and I said, well, that's really interesting, a bad hombre. He didn't say they're bad hombres. Hombres are men, bad men. An hombre in the art world is the gradient between light and dark. And I thought, well, he's so sophisticated. He understands this gradient of cross-border technology. And so we created a series of objects called bad hombres that use soil from the two places, that mix them together in different ways to talk about how an object can have a singular identity, but if you look closer, it has complexity built into it from two different soils, from two different places. In order to do that project in El Paso and Juarez, we had to develop a software system that allowed anyone to play with a robot, because a ceramic artist typically doesn't have the time to learn how to 3D model, how to use a 3D printer, and all those complexities. A ceramic artist has spent years developing their craft based on the tools that they have at hand. This is a new kind of tool, but we developed this as an online tool for creating pottery. It's called Potterware. And it allows anyone, it's available now, it's used in universities and high schools and colleges all over the world now, and anyone can subscribe to it and use this for 3D printed pottery. But allowing others to build these kind of complex objects has been very special to us in the form of democratizing these technologies in the same way that Earth is a very democratized material. Based on this knowledge of being able to think about these deviations, which we did not know what they were good for, we began to work with others in collaboration, like scientists, to think about how we can use these technologies for creating microhabitats for species that are in danger due to climate change. So we developed these series of nests for this bird that lives in the Farallones Island off the coast of San Francisco. And these bird nests, the birds are losing their habitat because the sea level is rising, and they no longer find these rocky crevices. So we designed this nest that allowed the birds to enter. They would be protected. It had to be strong enough so a sea lion would be able to be on it. It had to have holes in the bottom so that when they urinate, the waste can leave. It had to have a cap on it so that that scientists can get in there and get the chicks. So it had all these design constraints, very much like architecture. We're building a home for a bird. And so they've been being tested on the Farallones Island now for, I think, 6 years. We also worked with the Academy of Sciences, who've been developing, they realized that ceramic was a very good substrate for coral larvae to attach to. You may have seen in the news, like, you can dump a subway train or big pieces of metal or even weird shaped things in the ocean and then coral will grow. It's actually, none of that works. These scientists take a very different approach. They recognize that if one coral larvae can attach to one of these substrates and it has a habitat there that allows one larvae to prosper, it has areas of light and dark, it has a dimension where they can lodge into, and it can tumble around the ocean, and that area remains protected. They can close pack, so you can put them all in a boat and dump them into the ocean, or divers can dive down and pin them. So they had also lots of constraints for making a home for the survival of a single coral larvae. And we developed several different kinds of prototypes. We produced over 3,000. We're working with this group in hopes to create 1 million of them because they've been quite successful. And they're being tested all over the world in Australia.
No way to see you on the camera.
No, apparently I can't be seen in the camera. That was my strategy. So I guess I have to stand here now. But they're being tested all over the world. It's a really exciting project to think about how using the earth beneath our feet can influence the ecologies not only of humans, but of other species as well. They actually, before they release them into the ocean, they have to just sit them in the water, in salt water, for several months so they can acclimate and different kind of microorganisms begin to attach to them before they can place them in the ocean, and that's when they really become activated for coral larvae to be attracted to them. If you like books, I wrote a book with all this stuff in it called Printing Architecture and Innovative Recipes for 3D Printing. We call it recipes because we actually give out the way that we do this. We tell people, here are the formulas so that you can do it too. Again, this notion of democratizing these technologies so that anyone can participate in the making of objects that are potentially more sustainable, well, I believe there to be, than what is the current trend in 3D printing for the last 15 years, which is entirely plastic-based, or at the architectural scale, Portland cement-based, both of which are destructive to our ecologies and our bodies. We've had the opportunities to synthesize all these experiments. In this case, you know, we have aspirations not only to make ecologies for animals, but for humans. So, what year was this? This was about 6 years ago. There was a housing crisis in the San Francisco Bay Area, and they relaxed building codes so that anyone could build up to 1,200 square feet in their backyard without the consultation of an architect or without going to the planning board, which was a huge relaxation. I don't know, building codes have become much more stringent and tight. You have to do so much. But we use this as an opportunity to test at a very small scale many of these technologies in the development of a project we called the Cabin of 3D Printed Curiosities. We created a 3D printed shingled skin out of about 3,000 3D printed ceramics to make the waterproof cladding for the building that was hung on a 3D printed structure. Each of the shingles is actually digitally exactly the same. They're clones of each other, but we developed a system so that when they were manufactured, they'd wiggle a little bit so each one became unique. And we used recycled clay for the entire structure. On the front facade of the building, we used the grape skins, the salt, the cement, the sawdust to explore a different kind of tiling method using these recycled materials from the San Francisco Bay, holding plants that thrive in the San Francisco Bay Area, these succulents that use very little water. These photos are from a long time ago, but the building is still in great shape. In fact, we have to prune these plants because they are really successful. So this is the Cabin of 3D Printed Curiosities. Furniture is 3D printed. The interiors are 3D printed. Objects are 3D printed. We benefit from the translucency where the entire cabin becomes a lantern in itself that sets a mood, sets a kind of phenomena for the interior of the building. You can see 3D printed coffee, a pot made out of coffee, the wine globules, the furniture, this cladding system that is very much like a pressed tin ceiling, but where every surface is actually unique instead of similar, because it's not mass manufactured. This is at night. This is the transformation of that small little cabin into a place to sleep. And that's the cabin of 3D printed curiosities. And now, I think that I'm always wondering, when do we make the switch to move to the 3D printing of the Earth in a more robust way? And that has been the goal forever. And it's only been in the last 4 years where we began to make the reality of taking the soil underneath our feet and printing it at a much larger scale. At that time, 7 years ago, this was kind of the dream, that all those objects were actually aspirational scaled objects, models, to think, can we do this using the soil underneath our feet, using this 10,000-year-old traditions of Adobe. The first thing we had to do was invent a machine. I sent this schematic design to a company to see if they could make a robot that moved this way. That would be very inexpensive, and we collaborated over the course of a year, and we produced this robot, which is now sold everywhere. They've commercialized it. The beauty of it is it could make many ceramic objects at once, or it could make one big object. It has robotic parts that you find in some of the most expensive robots, but this machine only cost about $14,000 to make, which may or may not seem expensive, but a typical robot costs about $80,000, and you can't do anything with it yet. You have to then program it. You have to get all the parts. This became ready to go. We also had to figure out how to push large amount of soil through a hose, and that took many, many months to do. This is a manual 3D printer making these objects, but we're exploring ways to move soil through a hose controlled by this robot. And eventually, we developed a formulation, precision, and once we did that, we brought it back to the historic borderlands in Conejo County to, for the first time, build with mud in a radically new way, using robots. And it became an ongoing experiment that we called Mud Frontiers, because we're doing it in the historic frontiers of the United States and Mexico. And we're also exploring a new frontier of building technology that I hope can reintroduce us to our ancestral ways of building, since we've been disconnected from those ways of building, right? We don't get up in the morning every morning now and go out and build our crops, mend our house, add an addition to our house, all connected to a land-based practices. We get up sometimes, I don't know if you do, but we get up and we go to work somewhere. I imagine you all do, but this is probably a place where you probably have a greater connection to the land than most of the places that I lecture at. But there's a heritage disconnection that has happened, an amputation that disconnects us from our ancestral practices of building with earth. And so my aspirations are, and my hopes are, that this technology, while we might be still disconnected from the building of our buildings ourselves, we might be assisted by technologies that we can interact with. In other words, in the same way we democratize the software in an interface so that anyone can 3D print with clay, my aspirations is we can democratize the software so that anyone can design their building and participate in the building using robotic technologies, reconnecting us to a practice of earth and construction. Because for me, a building made of earth is not just a building material that we go to Home Depot and we buy a board. We don't know where this board comes from. We buy screws. We don't know where the screw gun comes from. For me, building a building made of earth means that we are digging from ancestral lands. We are connected to it with our hands or our ancestors' hands. And we have a cultural and traditional heritage relationship to that material. It is like a relative to us. And so I'm advocating for something different than contemporary construction practices. If you think about a typical building, walk up to any of these buildings, cut a section through it, you'll find that there is an exterior siding. It's probably a vapor barrier. There's probably a plywood sheathing. That plywood sheathing has glues in it. There's something that screws all that together. There's maybe a paint on that surface. There's an insulation. There's studs. There's wiring. There's conduit. There's plastic that wraps those wires. Keep going. There's sheetrock. There's the paper on the sheetrock. There is paint. There's all the associated tools that are very particular to each one of those materials. And there's all the expertise that is connected to the use of each of those materials. So you hire a painter, you hire a sheetrock guy, you hire a woodworker. There might be 30 different companies in materials alone that are represented within 8 inches of wall. Not to mention the tools that are used. And so the wall in contemporary construction is actually a real estate grab for thinness. All the companies want to find some way to insert their product in the thinness of a wall so they can profit from that. So when you build a building, you're building with multiple materials, with multiple expertise that come from who knows where. But what if we can move towards building again with one material that does the job of all those materials? So that's my aspiration. And these are experiments that I've been working on over the last 4 or 5 years, thinking about how we can take the soil from on the site, using a robot, and create structures. One of the first opportunities I had to do this outside of the lab, outside of the studio, was during COVID. I moved back here, I brought the robots, and I wanted to embark on a project that I called Casa Covida. Covida isn't really a word. It sounds like COVID. I built it during the time of COVID. Casa means house. Covida also sounds like cohabitation. This is a house for cohabitation during the time of COVID. It's an experiment in a multi-chambered room made entirely out of mud. 3 chambers have spaces for sleeping, spaces for cooking and warmth, the hearth, and a space for bathing and for reflecting on this relationship between earth and sky. All my architect friends tell me, well, this doesn't have a roof on it. I said, the sky is the roof. And they said, well, what kind of roof would go on a 3D printed structure? And I thought about this for a long time, and I thought an inflatable roof would be the most appropriate roof. So this big translucent pink roof structure that could be inflated when it rains, imparts this beautiful pink light, in this case, into the interior, and was like a cherry on top of this chocolate sundae. If you've been to Center and the Frontier Drive-In, I was invited to do an installation there. There was an experiment that allowed me to expand this experiment of Casa Covida to think about how large I could make. It's actually easy to make something larger than it is to make something small, because when we're printing, we need the material to dry. And so that takes time to dry. So if I'm making a small object, I can print a little bit, then I have to let it dry, then I can print a little bit more. But if I'm making something big, I can always keep printing. By the time I get back to that start, it's dry, and I can keep going and going. So Skylos is an experiment that's situated in the borderlands, situated in the frontier between the United States and Mexico, which is acknowledged by the Frontier Drive-In. It recognizes its location in the historic frontera of the United States and Mexico. And so the first thing we did to inaugurate the project was hosted a Borderland Film Festival at the Frontier Drive-In. The site, as you know, looks like this. There are all these center pivot sprinklers, and I thought it's so beautiful that the printer actually works like a center pivot sprinkler. It goes round and round. Doesn't mean that it can't print a straight line, because my goal is to print big and I have limitations. The biggest thing I can print is just to reach the arm as far as possible and to print. That's why things are round in my case. That's why things are round in this case too. And of course, you're familiar with all the silos that hold the grains that are grown in the San Luis Valley. And so I named this project Skylos because it doesn't hold grains, it holds the sky. And as explored earlier in Casa Corrida, it's the space that allows for this reflection between an architecture of the earth. We see all the potato cellars in that part of the county made of adobe, and its relationship to the sky, which is so important to us, that brings us rain and sun and light. And it defines sky in many different ways. And so there are 8 chambers, each of which are divided into 2 spaces. Originally, each of those spaces were intended to have a hot pool in them. So you would come to the Frontier Drive-In and you could soak. They didn't do that, but I wish they would have. Other things became more important. But this is the project under construction. And you can see that 3D printing a building is a little bit like a security job. There's nothing really happening unless something goes wrong. And so you see what looks like people just standing around. My very expensive graduate student there in the white shirt just looking, getting paid $30 an hour. But really beautiful and helpful. That particular individual there is now a professor at the University of Texas and has gone in his own directions with the knowledge that he learned from working on this project with me. I'll just let you enjoy some of these views of Skylos from above. Okay, thank you. And I think what's most important about this project is it's the first permitted 3D printed building in the world. We went through the building department, it was engineered, it went through all the regulations in order to be approved. So a big part of this goal and the work is not only our ability to do it, but our ability to do it through the legal processes of construction in the United States. I've been very fortunate that the success of this work has enabled me to scale up and to have a much more sophisticated robot that I was able to have manufactured over the last 3 years, which is still very portable, like the first one, which is not inexpensive by any means, but far less expensive than many of the 3D printing systems that you've seen that are bigger than the building that they build. But this recent experiment was an experiment to see if we can also build a roof out of mud. There's a technology that's thousands of years old that comes from northern Egypt and southern Sudan, where builders can build a roof entirely made out of adobe using no formwork, called a Nubian vault. And if you can see that, basically there's a wall that's built, and then the masons will stack adobes against it in the shape of a parabola, which is the shape your hand makes if you do that, which is the most efficient structural shape that brings gravity to the ground. They've been doing this for thousands of years. And ultimately, you build it forward, and you make an enclosed structure. I wondered if a robot could do that. I wondered if we could take the same kind of algorithm that a Sudanese mason would use and translate that using wet adobe. And so this is the experiment to see if we can make the world's first on-site 3D printed roof. Not only the first 3D printed roof, but made out of mud. And so you can see how it's printing at this angle using this robot that has 6 axes instead of the 3-axis robot that I had before. And slowly building forward. This pattern allows for a certain amount of friction so that the material can hold in place. And it prints until it encloses. And because mud isn't expensive, I don't mind that it spills a little bit, but you can see how it encloses off. And I'm flying the drone, I'm driving the robot, and my 14-year-old son is over there just making sure the hopper's full of mud. These textures prevent erosion from rain. It slows down rain. And there it is, entirely enclosed, the first 3D printed roof in the world. A little small, humble structure, but I think an enormous leap for thinking about how we might build buildings entirely out of earth in the 21st century. So as I begin to think about how to scale up, I'm imagining what what's next for this? How do we begin to print houses, architecture, buildings for people? And that I have not yet accomplished, but I'm beginning to do experiments that are operating at the scale that are very, very large. And using this robot, I simply wanted to see how big could I build a building just by one placement of the robot. And so Serpentine is that experiment. So that's just one experiment saying this is as big as this robot can make. But what's interesting about all of these experiments, and this one as well, is that we think of Adobe as a massive building material. The walls of my own house are almost 2 feet thick. But because I can deposit the material in this serpentine way, using these same curves that we explored in those very first ceramic pieces 8 years ago, I can make 10-foot high walls that are only 3 inches thick using the material. And that's an enormous benefit to thinking about how we might construct in the future. So most recently, just within the last year, I worked on a project for an exhibition called Desert X in Palm Springs, California, to design something called the Adobe Oasis. And this is the largest to-date thing that I've printed. It had to follow building codes and permitting and engineering within the city of Palm Springs. It's printed right downtown Palm Springs, even though it looks like it's in the middle of the desert. It just happened to be a vacant lot. And it takes on the idea of thinking about how we can work with the city, how we can work poetically, how we can work with a local source of material. And the material is really interesting because it comes from a mine within the county that provides all the soil for all the stadiums in the greater Los Angeles area. So it's an enormous material resource that came at a time when the very first layer of printing the structure was the day of the fires that burnt down LA. And so it began a conversation about how we might rebuild LA using these material systems and these material processes. And so I've been in a lot of beautiful conversations about thinking about how to rebuild there. There are thousands of Adobe buildings in the greater Los Angeles area already. The oldest buildings in California, just as in Colorado, just as in New Mexico, are all made of earth, the most celebrated buildings. And there's no reason why we can't reintroduce these building technologies and materials using a new way of building into our building culture. So I told you this lecture was about the 3 AIs. I've talked about ancestral intelligence. This is additive intelligence. And lately I've been thinking about how artificial intelligence might allow us to design more quickly. And what I've learned about artificial intelligence in the last 3 years is that the database of earthen buildings isn't present within the photographic record that AI draws from. And so we have to trick it to be able to communicate buildings made of earth, and especially buildings that are 3D printed made of earth. So it's just an artistic experiment, a design experiment that I've been exploring for the last couple of years, thinking about how we can create new kinds of possibilities for an architecture of the 21st century that's entirely made out of earth, that uses robotic construction, that connects us to our traditional and ancestral heritage practices, that is thermally responsive, that is non-toxic, and maybe allows us to imagine a better future that allows us to be connected to the earth in ways that we've been exploring for the last 10,000 years. Thank you very much. I think we have time for questions, maybe. We have 15 minutes for questions, if you have questions.
Hi, sorry. I'm just really inspired by the pit firing. I think I saw it in one of your videos. And if you've ever been interested in printing a kiln from like a high fire clay, like sourced in Colorado, or if you have any thoughts about that. I know like wood firing, and I'm a ceramicist and just really interested in building a kiln. And I think the like democratization of kilns is like future possibility, knowing that brick and like especially high fire brick is super expensive, and that Colorado has like high fire clay deposits.
Right.
It's an interesting idea, and that's what I
Right.
thought of.
No, I showed that example. I don't know. It's somewhere back here, but I have not explored high fire clay. A lot of those early ceramic objects are high fired clay, fired in a electric or gas kiln. Those structures, those ceramic objects that I showed, right? Well, they're there in that photo, but those are low fire micaceous clay that come from Taos and Picuris traditions. That guy there, he taught me how to do it. I don't know if you know who Johnny Ortiz is. He's a chef in Taos, and so he makes his own pottery. He taught us how to and where to find micaceous clay, and we 3D printed those as ceramic objects using the low fire clay and firing with cedar. And we did it in one of those structures made of mud, but no high fire yet. But there is a group in near Oaxaca, Tres Piedras, I think, that has a high fire wood kiln. But maybe it's not my goal in life to do that. This is enough. But making low fire pottery is really accessible and really possible.
Totally. Awesome. Thank you.
Yeah, thanks.
Thank you for that. It was fantastic. I was wondering about the political implications of this, because it seems like if you're scaling up, you've got a robot that can be maintained. You don't have a lot of workers. It was you, your grad student, and your son, and some of them. Is this something that can be scaled up to produce a lot of low-cost housing, for example, homeless shelters, that sort of thing?
Yeah, first I'll say yes, it's totally scalable, and that's what I would like to do. I think to enter into that realm, I already have people knocking at the door saying, we want 50 units in Taos, we want 89 units in Santa Fe. I need investment to do that. I mean, that's where I need to enter into the system of VCs or real estate development to do that, which is something I'm very interested in doing. But I want to offer, if I may, just a an alternative approach, because I want just to communicate this to everyone, is that, especially in the images I show at the end, that yes, this could be for low-cost housing. I would love that for it to be. But I just want to make sure that we understand that just because it's made out of earth doesn't mean it's for the homeless, doesn't mean it's for the poor. And I'm not, this isn't a critique of you or your comment, but I think it's really important to know, and this is my job that I haven't done a very good job at, is that designers, architects, myself, have to demonstrate that this building material and this building technology is a technology for everyone's 21st century lifestyle. That any of us in here, and I say I haven't done that yet because I would like any one of us to hear to say, oh, I want to live in that. I don't care that it's 3D printed, I don't care that it's made of earth. What I care about is that, oh, I can see myself in that building. And to me, that's the most important thing. And again, I haven't done that yet, but I just want to offer that I think there's this preconception that earth buildings suffer, which is that earth buildings are for the poor. And I don't believe that to be the case. Thank you. And not that this is, you know, the politics of this are immense. We have a president of the United States. We probably had more, but Ronald Reagan lived in an adobe house. Chairman Mao lived in an adobe house. Saddam Hussein lived in an adobe house. Doesn't mean any political ideology. There are very poor people who live in the house, very wealthy people who live in adobe houses. Look at Santa Fe. If you're wealthy enough now, you can afford adobe house. And that is actually one of the problems of the politics of Adobe, which is that codes have restricted the way that we can build traditionally. So imagine if you're a person who's been building homes in New Mexico for thousands of years, and it's been passed down to you. And suddenly, a code is in place that says, well, you know what? You can't have a stone foundation. You have to have a concrete foundation that's as thick as your wall that goes down below frost line. All of a sudden, you maybe have a 6-foot deep concrete foundation that's 2 feet wide. You can't afford that. And then you have to put a concrete bond beam across the top instead of a thin wood. You can't afford that. And not only that, you have to have these walls have I don't remember what, like 30 insulation. Why would you put foam insulation on a thermal mass building? It negates the need to even have a thermal mass. So therefore, you might as well build with frame. And even better financially, you might as well just go get a high interest loan for a modular home. And all of a sudden the codes kill tradition. That's the real politics of Adobe.
Any more questions?
Phew. So the implications of the, what's up with the mic? Okay. The implications of this to me from a design angle bring together years of experimentation in this area of the world to develop the perfect passive solar self-sufficient ecosystem. Year-round indoor greenhouse can be a part of that. Do you think that well, first of all, you're basically saying that if I know how an earthship works and I can take away the elements of it that no longer serve, that are too labor intensive and expensive, come up with a design, you could essentially 3D print the vault towards the passive solar glass enclosure, right? From the ground all the way up. That could be on a stem wall. So you're looking at a vault structure, which is the simple survival earthship. So all of those shelters, if you were to combine that, and also what Cal Earth does with the chimney tubes, convection. Have you ever printed a convection chimney?
These kind of operate like a convection chimney, but I did not intentionally.
Yeah. So all the passive systems, so that it's passive cooling, passive heating, and waterproof, tight enclosure is what you're saying you can achieve?
Yeah.
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 So you're just just one design away from a completely year-round passive dwelling structure that's 3D printed out of clay, because you have now the vault extrusion, which self-terminates, right? So you can do the entire extrusion and create a vault with glass face towards the south.
Yep.
Yeah, I'd love to do that. That would be sick.
Yeah.
We can do that here. No building codes.
Really? There's no building codes here?
Not in this county.
Don't tell anyone. I'll just go and shut you down. I mean, the possibilities are wide open, right? If you're making them, the first mud bricks are balls of clay that are shaped with the hand. They're cone ones, they're round ones, and you put them in place, and you have to work to do that. And you might be responsive in certain ways to your environment or your neighbor or the sun. Then people start making out of wood forms, and they're blocks, and they stack. Maybe rectangles are efficient. The 3D printer doesn't care. It doesn't care how long it works. It doesn't care how it's moving and wiggling around, which means what can you do with that? With all those wiggles we did in the beginning, we didn't know what those were good for, but we found they were good for micro shading, for load bearing, for ventilation, for drainage, for absorption of water. What can we do with all the forms and shapes we might be able to scribble out with a 3D printer? It's wide open. It's full of invention. Full of possibility. Don't even know yet what's possible, but it's wide open because it's like drawing. So it's taking a line for a walk. So instead of, if you're an architect, you draw a line on a paper, a blueprint, and that line tells someone how to build the building. Like that line is a piece of sheetrock, so the builder goes and puts sheetrock there, and that's what it means in plan. But the line for a robot means that's where I'm going to move. If you draw a straight line, the robot's going to go burp. If you draw a curvy line, the robot's going to go burp. If you draw that line three-dimensionally, that robot's going to do whatever. And it's going to spit out mud at the end. And there's amazing possibilities for that, for just thinking about windows, doors, responses to views and sun and wind. And yeah, it's wide open.
Can you talk a little bit more about the engineering? You mentioned that I think it was the one in Center was engineered and it was approved because of that. But are you working with structural engineers that have traditional training, or what kind of training is needed to do that?
So in the project in Center, the engineering had to do with first we tested the material. for compressive strength and tensile strength as well. So that was one part of it. So now there's an understanding of how strong the material is. And what I've discovered is that, how many of you are potters, by the way? So if you're a potter, you what is it called? You wedge the clay. And what you're doing when you wedge the clay is you're pushing the clay particles together tighter and tighter and tighter, which makes a stronger ceramic body when you fire the ceramic object. If you don't wedge, it's not as strong. The pumping system that pumps the adobe is compressing that clay down and pushing it through that tube. And I'm actually amazed that some of these experiments, which are just 1.5 inches thick, have survived the San Luis Valley snow and rain and cold for like 7, I think they're 7 years old, some of those. And they're just like 1 inch thick and they're 8 feet tall. And I was wondering, why? How is this possible? And I think it has to do with what's happening at a microscopic scale. So one is there's a material test. And then 2, there were wind tests on those structures, because in center it gets very windy, so we had to make sure they don't push over. And then, because we were going to put pools in them, they're all elevated up on stem walls, and they have an entire slab underneath that supports the load of those entire 8 pieces, so there's no heave and shift and that sort of thing. So those are the structural elements. Your last part of the question is, am I working with engineers who understand this material? In this case, this engineer wasn't. So it's all math. The math of the compressive strength, the math of tensile strength, it all works together to say this thickness is okay, this slab has to be this thickness. I'm working on a project now where the engineers really love Adobe, and they respect it, and they understand it, and they understand how traditional buildings are made, and they too, because engineers do this, they said, well, the math all works out. It's the politics that doesn't. And so how do we go to the building department and convince someone who knows nothing about Adobe that this works? And typically that's a stamp, but sometimes it's not a stamp from an engineer. Sometimes they just have to say, they have to believe, and there's a politic behind it. There's like talking to people that say, okay, you can do this. So the bureaucracy is challenging depending on where you go. Yeah.
I just had a question regarding insulation. I know one of the big limitations as far as building codes go is insulation value, R value. For instance, I think walls are R20, 25, the ceilings are R38 up to R49, which limits a lot because you have to have a certain amount of inches. Like for instance, hempcrete is 2.5 R value per inch. So as far as like when you're building with the machines, you have all these wonderful cavities. So have you experimented with, like, for instance, hemp or a natural material? Since obviously in the commercial world, it's fiberglass and pink cotton candy is what I call it, and styrofoam. But then all of these structures that are like green, what they're doing is spraying with the styrofoam, but after 20 years it turns into this like dust that's like this toxic just dust. And so have you experimented with insulation within these cavities?
I haven't experimented with it. I've only speculated it because I haven't actually the first roof I ever built was this summer. So I have a roof on a very small structure that I'm going to test heat transfer, but the walls are monolithic. But the unfortunate thing about the building codes is that they promote this idea of the R value, which is based on air. Like how, fiberglass insulation, all these things you mentioned are just filled with air, and air is insulation. And a monolith of earth doesn't have any air in it, but what it has is, as many of you might know, the capacity to store heat and release it slowly. And that's why Adobe buildings feel so fresh and cool, because they've been storing the temperature of the nighttime and then releasing it during the day. And all the solar gain that it gets during the day, it slowly releases into the house at night. And that's how there's this thermal flywheel effect. If you put insulation in there, you're actually stopping that cold and you're stopping that heat from moving through the building. And it becomes a different system. And that, to me, is unfortunate because it's not recognizing thermal mass as a performative value in contemporary construction. I called the building inspector in Conejo County the other day. I said, hey, you know I've been doing this stuff. Spraying a building with foam is ridiculous for many reasons. Also the reasons you mentioned, which all that dust, you know what happens to all that dust? Goes into our testicles, into our breast milk, into our brain, goes into our bloodstream. And so it's a problem. And so we have to change the codes where the codes enforce this. And the building code inspector said, hey, all the buildings here in Conejo County are made of mud. He said, well, you know what? We can do exchanges. We can insulate the roof more so you don't have to insulate the walls. Or we can put better windows or better doors. It's an exchange, it's a compromise, but I still think it's a little bit of an unfortunate compromise because that means you're loading up other areas of the building, which is more expense and not engaging the thermal capacity of the wall, of an earthen wall. Yeah. Okay. Hi. I'm going to let them decide.
All right.
Okay.
Okay. So, I hate to ask this question, but I like your presentation. It's been eye-opening. I've seen the skylos, and they're incredible and they're beautiful. What is the cost of entry to erect a small structure like this to live in here in this valley?
It's a good question. It depends. It depends. Okay, so I'm the only guy who can do it right now. There's what's that?
Well, there's the robotic. There's the machine cost.
Yeah.
The material cost we understand, like, it's not that much.
Yeah.
But and there's no labor cost. But well, you don't have to talk about that, the mechanicals. But as far as the robotics and, like, if you were to build here in the valley, what does that look like? Is that feasible?
You know how much this costs in materials? This thing, it costs $40 in gasoline. That's what that cost. That serpentine, I don't remember what that cost, but that part is cheap. But walls aren't necessarily the most expensive part of a house. All those other things are. Also, I'm doing this in a very boutique way right now, which means things you buy in boutiques are expensive. Only because I'm a fancy guy. I wish I could just go to every one of your houses and just dig the dirt and print and dedicate my life to that. But if I am able to scale up and I have a fleet of robots and I have a crew and I can dispatch them into the world, I think I'd lower the cost of construction by at least half. Find that crew? Yeah. Okay. Yeah. Okay. Yeah, totally. It's not labor intensive. I mean, I've automated the mixing now. There's still some labor, but I'm actually trying to get rid of the labor. And I don't know, usually when I lecture, people say, well, what about labor? Labor is really important. Labor, I don't romanticize labor. As someone who's labored all my life, I actually don't romanticize it at all. My back hurts right now. My dad's back hurt, my grandpa's back hurt. I saw them creaking around. I don't jive with the notion that people say, oh, well, the labor, the community. Community's good. There can be community around robots. I showed it in many cases, but building more safely for your body, enjoying other things. What I saw a cartoon. Let's see if I can remember it. It was about AI, and it says, I'm gonna have to think about how this went. I want AI to do my dishes so I can make my art, not make my art while I do the dishes. I think that's the same for robots. I mean, I want to see if the robot can allow us to alleviate construction, reconnect us to a heritage practice, so we can also do other things. So we can plant gardens, so we can enjoy life, enjoy our kids, that sort of thing. Yeah.
That's all the time we have.
Okay.
So thank you so much, Ron.
Yay, thank you.